So another way to solve transient heat transfer problems is using using Heisler charts. So Heisler charts correlate dimensionless temperatures to dimensionless numbers, such as the Fourier number, which I call tau, which is a function of time. So this can be a useful relationship for finding temperatures after time, or times if you're given a temperature. These are really useful correlations. And they eliminate some of the really gross solutions or even impossible solutions you might have if you try to analytically solve some of the differential equations involving time. So it's a really convenient solution. And as well as that, you have you can account for materials with lower thermal conductivities. So if you have a material that might not fit well to the lumped capacitance model, this can help. And this is still a very simple solution. So let's look at a case for a cylinder. So this is a plot graphing the center temperature, or axial, for a cylinder, for a long cylinder, and it's plotted against Fourier numbers for given Biot numbers. So let's do a problem. What is the center temperature of my rod after 30 seconds? Compare that result with lumped capacitance, and we're given a bunch of values. Now note that our thermal conductivity is very high. It's about 600 watts per meter degree Kelvin, which is very high. So here, that alongside the fact that we have a pretty small radius, this isn't a huge object, we'd probably expect lumped capacitance to be a decent approximation. So let's do both of these calculations. Let's figure out what the final center temperature is going to be, and then let's compare them. So let's go ahead and start with the Heisler chart method. So we want center temperature, so the output is going to be the y-axis here after 30 seconds. So given 30 seconds in all of our variables, that means we can calculate tau. So let's go ahead and start by calculating tau, and then we're also going to need a Biot number, and then with tau and a Biot number, we can get a dimensionless temperature. So let's go ahead and do that. So let's start with tau. We know tau, the Fourier number, is alpha over characteristic length squared times time, which we will call characteristic length the radius. Let's go ahead and solve. Let me give me more room here. Let's go ahead and solve alpha. Alpha is the thermal conductivity over the density times the specific heat. All those values can be looked up if they're not given to you a problem. For like a known material, those can generally be found online or in reference materials. Okay, so anyways, it's going to be 600 over the density, which is 5,000, times the specific heat, which is 250. Throw this into our calculator. 600 divided by 5,000 divided by 250 is 4.8 e to the negative 4. And that's expected. Alpha values are usually pretty small. So let's go ahead and solve tau now. Alpha, we can put that in the numerator, over our radius squared, which is going to be 0.04 squared, times by our time, which they told us was 30 seconds, and seconds are SI units. So I'm just going to keep everything in SI units, and I'm going to ignore units. Okay. Alpha divided by 0.04 squared, times it by 30 seconds, you get a tau of 9. Now let's calculate our Biot number. Biot number, remember, is the heat transfer coefficient times our characteristic length over K, and we called the characteristic length R. So let's go ahead and calculate these. 600 radius is 0.04. Thermal conductivity is 600. So the 600 just cancel, and then we get a Biot number of 0.04. Okay, so now we have a tau of 9, a Biot of 0.04. Let's go ahead and solve this. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're on this line. And then our Biot is 0.04, which would be just above that. So the line would probably be something like this or something. It doesn't matter too much. We'll just kind of ignore it. It'd be like somewhere right there. That seems like a decent approximation. Let's follow this line over. This is 0.2, 0.3, 0.4. Looks like it's almost exactly 0.5. You know, in this, it's like a logarithmic scale. So it looks like it's about 0.5. So our dimensionless center temperature for our cylinder looks like it's roughly about 0.5. And remember, the definition of dimensionless temperature is temperature at some t, which we know is we're solving for 30 seconds, minus by your ambient all over your initial minus your ambient. So for us, this is just going to be, we're going to plug in our values. For the ambient, they tell us that's 300 degrees Kelvin. Initial 600, ambient's 300 again. So we can take our 0.5, times it by 300, which is that denominator, add 300, and we get a result of about 450 degrees Kelvin from the Heisler chart method. Okay, so there's a result. Let's see, we're actually we're exactly halfway between our ambient and our initial temperature. So after 30 seconds, we're exactly halfway. So that's interesting. So now, like I mentioned, with such a high K value and a relatively small object, lumped capacitance should be a good approximation. And so let's go ahead and solve with lumped capacitance and see how they compare. So remember, the lumped capacitance model says that our temperature over our object is consistent throughout. So now we're not worried about center temperature, surface temperature. We don't really care. It's just all 1 theta. And we say that that is going to be equal to the exponential of negative n Biot number tau. And for a cylinder, n is equal to 2. For a plane, it would be 1. For a sphere, it would be 3. That's just a piece of information. There's another video on those values and exactly how the lumped capacitance model works. And then we knew our Biot number we already solved for, which was, what was that, 0.04. Same with tau. We already solved tau, which was 9. So let's go ahead and throw this in. Theta equals the exponential of negative 2 times 0.04 times 9. Throw that into the calculator. 9 times 0.04 times negative 2. Take the exponential of that, and we get that theta. After, we'll just call it theta. It equals 0.486. 8, we'll call it. And then let's, our dimensionless temperature is defined the same way. So T of 30 minus 300 all over 600 minus 300. So same as before, let's take that 0.4868 times it by 300, add 300, and we get a T after 30 seconds of 446 degrees Kelvin. So if we compare our results, now this is from lumped capacitance. So if we compare these two different ways to approximate, they have extremely similar results. Now, if we had an extremely low thermal conductivity, that'd probably not be the case. They'd probably diverge quite a bit. But yeah, this is a sample for how to use Heisler problem or Heisler charts for a long cylinder and how it could compare to lumped capacitance. Okay, so another convenient way to solve transient heat transfer problems is with the Heisler charts, which I have here. So I pulled these from the book I was using, and these Heisler charts relate dimensionless temperatures to some of our dimensionless numbers. So on the left here, this is the dimensionless center temperature plotted against our Fourier number. So the book I'm using actually calls the Fourier number x, but I've been calling it tau. So we'll call that tau. And then you can get, you can relate those two. And then we also have another one that relates center temperature divided by surface temperature, so that's what this is, over our Biot number. So these can be convenient for getting graphical solutions, and these can be a little more convenient than trying to get analytical solutions, which become difficult with these transient problems. So let's look at a question. For a sphere, how long will it take the temperature of the center of the sphere to reach 100 degrees Celsius, and what is the surface temperature at that moment? Okay, so they give us a final center temperature, which is 373 degrees Kelvin. They give us a ambient and an initial. We can solve a dimensionless center temperature, which of course is going to be the final temperature. Oh, here, I'll do this. T minus TA over the initial minus T ambient. And that's going to be 373 minus our ambient, which is 300, all over 600 minus 300. Throw that into the calculator, and you get 0.2433. Okay. So now we have a dimensionless center temperature. So if we're using this one, that's going to be roughly like here-ish. And then in order to get the tau, we're going to need the BO number. So let's go ahead and calculate the BO number. We know the BO number is H characteristic length over K, and our characteristic length is the radius, since we're using a sphere. So, and we have all these values. Let's just plug these in. 425. Our radius is going to be 0.05 meters. You're going to want to keep it in SI units. K is 50. Okay, throw this into the calculator. 425 times 0.05 divided by 50. 0.425 for the BO number. Okay. So our BO number it's around that line, not exactly. It's between these two BO numbers, so it's probably something like this. But we can pretty much just use the 0.5 line. And then our dimensionless temperature is at 0.2433. So then if we go over something like that. So let's see here. Looks like it's around a tau of 2. Right? It's like a tau of 2. Okay. If we know tau is 2 from the Heisler chart, now we can solve for a time with tau, because we know tau, the Fourier number, is equal to, alpha over our characteristic length squared times time. And we know alpha, which we're going to have to solve, is K over rho CP. And let's solve for that right away. Okay. 50 divided by 8,000 divided by 200. We get a small value for alpha, which is expected. Okay, and then let's see. So now tau becomes this. Our characteristic length squared is 0.05 squared times time, which we know equals 2. So multiply over 0.05 squared, so 2 times 0.0025, divide over alpha, and we get a T of 160, and this, since this is in SI units, this is seconds. And if you want to get that in minutes, that could also be 2.67 minutes. Okay, first part of the problem done. What is the surface temperature at this moment? So now we know the center temperature. We also know a BO number, we know a tau, we know a lot of stuff. We don't know the surface temperature. So now we can use this chart. Let's find our BO number. Our BO number was 0.425. which is going to be around here. I'll just call it roughly. And on that line, that looks like, what is that, 0.85-ish. So here, let's write this. So now we know our dimensionless center temperature over our dimensionless surface temperature is equal to 0.85. And we know our center temperature is, we know that it's 373 degrees Kelvin. Actually, I wrote this wrong. This is actually surface over center. I wrote my plot wrong. Okay, this is supposed to be, this is surface. This is center. I had it backwards. Okay. So now, if we know that our dimensionless center temperature, we already defined to be 0.243, we can just multiply that into our 0.85, and we see that the dimensionless surface temperature is going to be equal to 0.20655, which is equal to T minus temperature ambient, which is 300, all over 600 minus 300. And so now we can solve for T. So basically take our result times by 300 and then add 300. And our temperature at the surface at that final moment is going to be 361.9. We'll just say 362 Kelvin. So that's a quick example on how to use Heisler charts. And let's see, I had this one backwards, but I just wrote it wrong.